Okay, so we'll go through the uh, Common Core Regents exam from June 2015, and we'll try to show you how to do each of these problems. So the first problem is about a 3D shape that will be formed if we took a two-dimensional shape and rotated it around this leg right here. So if we took this and rotated it 360 degrees around that segment, uh, T and all the points from here to here, from R to T, would all move around in a circle around that. You have to use your spatial reasoning and imagine what that would look like. So the path of T would be a circle that basically comes out of the page and back through. What would that form? Well, you'd have a circular bottom. ST would be the radius of it. And then, the whole side of it, RT, would be rotated around. So that would make altogether a shape of a cone. So that would be our answer, choice 4. All right, now we move on to number 2. Um, so what we're looking at is um, under which transformation is the image of a figure not congruent? Well, what we're going to do is there's rigid motion transformations. And that would be your line reflection, translation, point reflection, rotation. So that would be your rigid motion transformations. Um, which ones? That would remain congruent. So that would produce congruent figures. Okay. Now, the ones that would not perform congruent figures, so change the size. These would be dilation and stretch. We don't study stretch a whole lot, but those would, those would create images that may not be congruent to their pre-images, depending on the scale factor we choose and things like that. So translation's out, a rotation is out, reflection over the y-axis out. There we go. Dilation with a scale factor of 2, centered at the origin, will definitely change the size. So choice 4 is what we want there. Okay, number 3, we've got to plot the center of a circle Q. So let's go to 3, -2, label it Q. And let's see, if circle Q passes through a point R at 7, 1. All right, and we'll attempt to make a circle that distance. Hopefully you have your compass tool that will do a lot better than what I'm about to do. But that's what it's basically going to look like. What we're saying is QR is the radius. So they want us first to understand that, comprehend that. Second, now we essentially have to find the length of QR and double it. So some people use the distance formula. What we tend to do in my class is we use right triangle Pythagorean theorem. So we'll count the squares, 4 this way, 3 that way. I'll go through the Pythagorean theorem, but we hopefully know that it's going to be 5. This is going to be 25. Square root both sides. And we get a radius equal to 5. So if the radius is 5, don't forget, diameter is going to be double that. And we get choice 3. All right, moving on. So to number 4, we're looking for a sequence of transformations to map one figure onto another. Now, it goes in order. We have to understand the notation here. A to A prime. B to B prime. So this is our pre-image, or our starting figure, and then this is the first image. And what it looks like is the slope stayed the same, orientation looks like it's going to be the same. Whoops. Um, Everything appears to be the same. Hopefully it's obvious that all of these points moved in the same direction, same amount. When that happens, same directed segment. Um, so A to A prime, that's the symbol for directed segment. B to B prime, those are all congruent. When that happens, as well as parallel, congruent and parallel. When that happens, what was performed was a translation. Okay, the translation vector is any of these, A to A prime. Now, after that, what we're looking at is, let's see, translation was first, so get rid of those. All right, was the move from A prime to A double prime, was that a reflection or rotation? Now, if we take a look at that, as far as point reflection, I doubt it. That probably did not happen, but a rotation centered at the origin does seem reasonable. Looks like probably a negative 90 degrees. So looking at a couple different image, pre-image combinations, it looks like it is a negative 90 degree rotation centered at the origin. We're going to have to go with that. A line reflection just doesn't make sense there. So that's going to be choice 4. All right, number 5. What we have appears to be a trig problem. Okay, we have a right triangle, a angle measure. Usually that's not going to be Pythagorean theorem. So let's take a look here. If the point is 20 feet from the base of the tree. All right, so some vocabulary. 20 feet from the base of the tree, looks like that is going to be what they're talking about, the side they're talking about. What's the height of the tree? Let's call that H for height. And this is a standard right triangle trig problem. So what we usually teach is identify the hypotenuse, identify compared to the angle, acute angle that's given. We like to identify opposite and adjacent. Let's see. It looks like opposite and adjacent are the sides involved. So if we go to our helpful acronym, SOHCAHTOA, we can see that, and this is confusing sometimes for students, what this means is the first letter is the trig function. Sorry about that. First letter is the trig function. Second letter is on the top of the fraction, and the third letter would be the bottom of the fraction. So to write out these trig functions, you need tangent of some angle, it's a function, equals the side it's a ratio of two sides. Tangent is the ratio of two sides, and it's the opposite side over the adjacent side. Okay, now what we'll fill in is tangent of 34 degrees equals, we don't know the opposite side, we do know the adjacent side is 20. Now we'll go to the calculator. I'll have to type in tangent. Sorry, you can't see what I'm doing here, but you'll have to go to your calculator right now. Hopefully you're typing in tangent of 34. All right, what my calculator gives me is 0.6745, and there's some other stuff after it. So I don't round yet. What I teach my students is that a trig function is the ratio of two sides. So when it gives us a decimal, I like to teach them to put it over 1. So it's still a ratio of two sides, ratio of two numbers. Now that's going to equal h over 20, and now we can cross multiply. No, that's not the best thing to call it, but that's what we're doing. 20 times the 0.6745, and whatever is left in the calculator. So hit your calculator, multiply the answer by 20, and what we get is 13.4902 and so forth. If you get something different than 0.6745 out of your calculator, you might be in radian mode. So go ahead and make sure that you change your calculator over to degree mode. Um, all right, so the nearest tenth of a foot, we've got to round that to 13.4 feet. Just check units of measure. Yes, it is feet right there. So no trick involved. Um, that's not good. That's not a choice. Let's see. Oh, 49. I'm sorry, I read this wrong. I skipped a 9. That's why. So it's 4902. That would round it up to 13.5. Now I get it. We got that choice. All right, number 6, cross section. Cross section. All right, this is in our volume surface area topic. So it'll be chapter 9 from our course. The sphere cross section. So basically what we're looking to do is we're looking to slice through a sphere, a basketball, tennis ball, whatever. If you slice through a sphere, what we get is the cross section is going to be a circle. You'll get a flat surface, and the 2D shape you're looking at is the circle. Now, if we slice through this figure, you might get a triangle or some shape that's got segments for sides. But you're never going to get that curve that you need for a circle. So none of these are going to work. Okay? When you take a polygon and slice it, you're going to potentially get trapezoids, triangles, rectangles in some cases, squares, parallelograms even, I don't know. There's all sorts of different things you could get. But without some kind of curved surface, there's no way to get a curved surface, such as a circle has. So the only one that's got any chance is choice 2. Now, if we could take a cone and slice it this way, assuming it's, well, try to make it look like 3D. If we could slice through the middle of the cone parallel to the base, the circle at the bottom, we would basically move up the cone a little bit and we'd get a circle as the face of it. So we're going to have to go with the cone's the only one that's got a shot there. All right, number 7. What we have is looks like a 2D rectangular prism, 3D rectangular prism. So best to sketch a model. That's definitely something that will help us make it look a little nicer, easier to work through the problem is if you have a model to work with. Okay, so reading through this, you have a length of 12. Let's just call the distance from the front of the container to the back of the container. We're going to call that our length. The width we'll say is across the front, and the height we'll say here to here is 4. Whoops, so that's the height, we'll call it. So I'll put numbers on another one. Okay, so we're going to have a length of 12, a width of 8.5, and a height of 4. Now, completely filled, that is kind of showing me volume. That's what I'm leaning towards. When we fill a 3D shape, you're probably talking volume. Now, the volume of a prism, if we look at the formula sheet, I think it's going to be capital B times H. That's really, the B is the area of the base. Now, we get to pick in a case with a rectangular prism. I'll call the base this 8.5 by 12 rectangle. Okay, so the volume is going to be the 8.5, so the area of the base, 8.5 times 12, because it's a rectangle, so length times width. And then basically what I like to teach my students is imagine that you had 4 of these that were 1 foot thick. That's essentially what we're going to get here. So type those into your calculator, 8.5 times 12 times 4. We're looking at 408. Now, of course, that's a trick. There's 408 as an answer, but make sure that we're fully working the problem. Common Core loves to make sure students are fully working the problem. Make sure you're answering what they asked for. Now, here's what I mean. On average, a quarter pound per cubic foot. Okay, so this is how many cubic feet we have, 408 cubic feet, but the weight is 0.25 pounds per cubic foot. Here's what that means. It's 0.25 pounds. Now I should say lb, but not everybody knows that, so I won't confuse us more. For every 1 cubic foot. That's the ratio. Now, if we have 408 cubic feet, here's what we're going to do. We're going to take the 408 cubic feet multiplied by 0.25 pounds to 1 cubic feet. 1 cubic foot. Now, this is kind of a science way of doing it called dimensional analysis. What's nice about this is if you have feet cubed in the top, feet cubed in the bottom, they knock each other out. And what we're left with is whatever we get when we do 408 times 0.25 divided by 1. Okay, so let's try that. Oh, I could do that in my head. It's probably 102, right? So a quarter of 408 is 102. Now that's how many pounds would be in the container right there. So that's what we're looking at. All right, next. Number 8 is a circles problem. Now, what we have here is, which statement is not always true. What we got to know is when we have a situation inside of a circle, this angle C and angle F are inscribed angles that open up to the same arc. What that means is those angles are congruent. Okay, inscribed angles, they have a vertex on the circle, and they're basically 2 chords of the sides, so they open up to this arc. Well, angle C opens up to the same arc, so those 2 angles must be congruent. Now, of course, we have our vertical angles here. So these 2 triangles are similar. What we're going to get is sides that are proportional, corresponding angles are congruent. Okay? So let's take a look. CEG, angle CEG, that would be this one. Is that congruent to angle FDG? Yes, that is. They're, again, inscribed angles opening up to the same intercepted arc. The triangle CEG, just follow the path. Yes, that's the similarity statement. That's true. Which one's not true, remember? Do we know for sure if CG is congruent to FG? No, we don't know for sure. One last check. Let's see. Proportional, so CE to EG. FD to GG. Yes, those are, whoops, that's true. So corresponding sides are proportional. These are always true. This one may or may not be. So that's our answer. Choice 1. All right, let's try 2 more for this session. I know it's getting pretty long, but we got to get through a few of these. Perpendicular line, what we have to know right away is we need slopes that are negative reciprocals. Okay, now what I would like to do first is find the slope of this original line. So careful here, this is some algebra where a lot of mistakes could occur. Okay, if those subtract 2x, but this is tricky right here. That's negative y that comes down, equal sign, and be careful here. This should stay negative 2x plus 7. A lot of mistakes can happen there too. Let's divide everything by negative 1 or multiply by negative 1. Okay, we get negative over negative is a positive. Sorry, it's going to be minus 7. Really, the key is the slope of this line is going to be 2 over 1. So for a perpendicular line, we need a slope that is the negative reciprocal. So we got to flip it and change the sign. This has a positive sign, really. We have to change to be the negative reciprocal. We have to say negative 1/2. Now, make sure you're saying negative reciprocal, not opposite reciprocal. All right, so look back in our choices. That one's out because the slope is 2. Negative 2, that's out. Positive 1/2, tricky, out. And that's the one we need. It has a slope of negative 1/2. Remember, we're in the format y equals mx plus b. The slope is whatever we multiply x by. All right, almost done with this video session. We'll just get through the first 10, and we'll get the other ones after. All right, which regular polygon? All right, so regular polygon means all sides are congruent to each other, and all angles in the figure are interior angles, are congruent to each other. All right, so basically what we're looking at is carry on to itself is another topic too. Carry on to itself, it's basically what we call symmetry. So we want rotational symmetry. So if we, to achieve rotational symmetry, that's why all sides and all angles have to be the same. Makes sense. Now, basically what I like to do is, if we were to take a circle and we were to move a point along here, what it's got to be is we've got to map each point onto itself within 45 degrees. Well, the whole way around is 360 degrees. So if we only need 45 degrees to achieve a match or map it onto itself, it would take 8 different points. So let's see if we can, I'll try to sketch that. That looks like I'm going to get to 6. Let's try and make it a little tighter. Yeah, you get the idea. Let me get rid of that. Should have done that a different way. But if you want to do that, what we're going to need to do all right, that looks a little better. So that's going to be a 45 degree. We need 8 of those to make it. That's going to be an 8-sided polygon, which is an octagon. All right, that'll take care of our first session. And check this out. See if this helps you get through our first practice exam. Thanks for tuning in. Take care.